Good, so picking up where we left off, we're just taking a look at some exercises in the complex plane. And let's try a few. Let's see. I would say there's a shortcut. Sometimes we need to write numbers in terms of the exponential functions. How to write all exponents in a form using e. This comes from the fact that if a to the b is a positive number, then you can rewrite that as e to the natural log of a to the b. And why would I do that? It's because what happens in the exponent is that you end up multiplying b times the natural log of a in the exponent. And so exponentiation of a base to an exponent turns out to be multiplication, just normal multiplication in the exponent for the exponential function. Good. And so, for example, what is 2 to the I power? Well, in order to understand that, we'll go ahead and use our trick and exponentiate that. So it's e to the natural log of 2 to the I power. I'm going to kind of brush over the idea of having a non-negative number there. Maybe I shouldn't have mentioned it, e to the I natural log 2. So you notice that is e to the I theta power, right? And so how do you rewrite e to the I theta? That's cosine natural log of 2 plus I times the sine of the natural log of 2. Good. So this is what it means to take 2 to the I power. What does the square root function mean in complex arithmetic? Well, you can rewrite that in exponential form, right? And as soon as you write it in exponential form, you can rewrite it as 1 plus I to the 1/2 power, right? And actually, it's probably easier. Well, we're kind of doing it now. You're going to take e to the 1/2 times the natural log of 1 plus I. But of course, what's the natural log of a complex number? You have to rewrite that in exponential form, or in what form? Polar form. And so I could have just rewritten this in polar form to begin with. So alternative route is to take 1 plus I and rewrite that as the square root of 2 times e to the I pi over 4. And now if I take the square root of both sides, now this is already in exponential form. So the square root of 1 plus I is the 4th root of 2 times e to the I pi over 8. Good. So that's kind of fun. Similarly, you can ask yourself, is I to the I defined? That's kind of an odd thing, because it's a complex base to a complex power. What does that mean? Well, you can always rewrite it in terms of the exponential function. And so that's e to the I times the natural log of I. And now what is the natural log of I? Remember, in polar form, where is I? It's right there. And so r here is equal to 1, and theta is pi over 2. And so therefore, the natural log of I is equal to the natural log of e to the I pi over 2, right? And so that's going to be I pi over 2. Good. And so what does that mean? That means we have e to the I times I pi over 2, which is e to the minus pi over 2. This is a real number. I to the I power turns out to be real. Pretty weird. Okay, enough of the weird. It is fun to try these. There's more on the exercise page that you can check out. One thing I do want to do as well while we're doing this is do a little bit of algebraic review. The idea here is that when you're trying to solve these quadratics, it's a lot easier to complete the square than it usually is to use the quadratic formula. So don't use the quadratic formula just as a general rule of thumb. Don't use the quadratic formula unless you have to. Unless you're running into some really nasty fractions and you want to convert everything to numerical values. Use complete the square because it will typically be easier to use. Okay, let's see what I mean by that. So suppose I've got x squared minus 2x plus 6, and I want to solve that for that equal to 0. So I can rewrite that as x squared minus 2x plus something, and then I'll bring the minus 6 over. And so we see, remember what to do? You take half the middle term squared, so that's going to be half the middle term is minus 1, squared is plus 1, and then you add 1 to both sides. And so that makes the perfect square on this side equal to minus 5. And so there you see your quadratic, or your complex number, right? So that means that x minus 1 is equal to plus or minus the square root of 5i. And then you see that x is equal to 1 plus or minus the square root of 5i. Good. So similarly, if we had r squared minus 2r plus 6 equals 0, right, as our characteristic equation, then we know that r is equal to 1 plus or minus the square root of 5i. And do you remember how to write down the solution to the difference equation now? This is, I'm sorry, I just jumped ahead. Let's pause on that for a second. I just did the other video and I just had a flashback, so we won't worry about that one. Okay, I think, you know what, I'm going to leave this here and let you work on those exercises at the end of the handout. And the solutions to those exercises are on our class website. Okay, have some fun. Once we get through this in other courses, we might, if you get into complex analysis, there are beautiful things in the complex plane that you can work with. Something called the Riemann sphere. You might check out YouTube on that. There's also something called Julia sets, the Mandelbrot set. There's all kinds of fun and interesting things happening in the complex plane. All right, I will stop there and finish up your section 3.3 videos in the other thing. Okay, I need to stop now.